So I want to make sure that I record this. Okay, welcome to this lecture. For today's lecture, I'm going to focus on the second law of the thermodynamics and also going to talk about the entropy, which is one of the property that we use to describe the second law of the thermodynamics. I'm going to show you a couple of examples. But before I do that, I wanted to share the screen to tell you where you can find the information, and I will show you my notes. Let me open that first. Okay, right now on the screen, I'm showing you the Canvas. If you go to Canvas, again, the honor section, you should watch the video in the honor section video here. Example is over here, and we only have a few weeks left. We are on the week 13, and today we are going to talk about the second law of the thermodynamics and entropy. If you click on this link, then we'll bring you to a page. In this page, I give you kind of guideline how you prepare or understand the material for this topic. We will show you some of the pre-lecture videos that you're supposed to watch from the sapling system. And then these two videos are the video that I think is mostly helpful if you couldn't understand the material from the pre-lecture videos. And these two explain it very well. And then today I'm going to show you some examples. So after the class, I will post the link at here, and you're going to see, if you watch the video of today's, then you should be able to see some of the examples to show you how to do the calculation. So in the future, I will try to create this kind of a web page. Hopefully this will guide you through to prepare and understand the material that we try to teach you. Let me go back to the calendar because there are a few things. Since we only have like less than a month left, and you still have like 2 exams. As I said, Monday we're not going to have an exam 3, but I'm going to do the exam 3 review. So I'm asking you, unless you have things you have to do, you couldn't join me. Well, I suppose that you should be able to join me because you're supposed to have the exam 3 on Monday. I will walk through some examples in the exam 3 practice exam, give you more clear idea what you expect for the exam 3. So we probably will use the workout rooms, so the breakout rooms, so you guys can practice on your own. I hope that this exam that you will do much better than the previous 2 because we don't have time to give you the correction again. So the exam 2 correction will be the last one for this course. Your exam 2 correction, I sent you the link already. So you click on that link, you should go to the correction page, and it will be the same thing as you did previously. You pick the question that you wanted to do the correction, and I will take the average from your original and also your correction, and that will be the point that you get for that question if you made the correction. Then I will calculate the final score for that exam. I did not drop any of the exams. So there's a lot of way that you can make it up. So I do not drop any one of them. As for the rest of the semester, I mentioned it before, we still have like 2 chapters after this chapter 15, but we probably won't have time to finish the rest of the 2 chapters. So I will focus on chapter 12 and chapter 13. I'm going to just spend 1 lecture to give you the idea about the wave function. So that will be I will point out what will be the thing covered in the exam. And if we have time, and then I will probably use some of the time in the last day of the lecture to go to start a review. The Monday on the last week, I know some of you probably have to prepare for the final. I'm not sure that you will show up or not. I will probably record some of the video to review the important things for the whole chapter, for the whole um, physics one. So you will get a more precise idea about what the final exam looks like by watching the video for the final review. I will tell you what kind of problem that you expect to see for the calculation part. So if you wanted to get an idea, you should watch those videos. So I don't think that you guys will come, but if you have a question, you are more than welcome to join me in my office hour, or if you still wanted to, you want to have the person-to-person talk, you can also send me the email. All these overall review will be the video, so I will probably make all the video available on before the finals week, so you can watch those video on yourself. The final exam is not on Monday. The final exam is the last day of the lecture, which will be on Friday, because I know you have tons of different exams you have to prepare. And we are going to have the comprehensive exam, so it's going to cover all the material. And that's why I want to give you more guidance about how you prepare. So the final exam is on Friday, and it's going to start in the afternoon. So you come to school and it will be at the same GE building. And I think we will start exam at 2. So if you come to school Friday afternoon from 2 to 5, then we are going to have the final over there. All right. So that is the things that I wanted to kind of give you a heads up what happened for the rest of the semester. Now, we're supposed to have one more lab. Unfortunately, because I delayed the exam, we are not going to have the last lab. The last lab is about vibration, which is the new material for the next week. It's going to be the chapter 12. Okay. Any question from people online now? If not, then let me show you the material for today. Here I'm sharing my notes. The topic for today is about the second law of the thermodynamics and also the entropy. Now, in the pre-lecture, if you watch the video, and I hope that you watch that, there are some of the things in the video I would not give you the problem on that. And the things I would not ask you is about the engine and also the refrigerator. That is more like a mechanical, more like a physics. So you're not going to have those kind of question in your exam. The things I will include from that part of the material is going to be the definition of the efficiency. So the efficiency has a very simple equation, and it depends on the temperature. It also depends on the heat. So let me write down that equation over here, and let me open my pad to write that. While I am preparing for that, let me kind of review the things about the thermodynamics law. We have 3 different thermodynamics law. Actually, there's a 4. The first law of the thermodynamics is talking about the conservation of the energy. And there's a the zeroth law, which is about the thermal equilibrium. So in the coming exam, you're going to have one problem about the thermal equilibrium. Then you have two objects or more. They have contact with each other, and they're going to change the temperature. They're going to have the temperature to be equilibrium. So the thermal equilibrium is the zeroth law of the thermodynamics. And the first law of the thermodynamic is the conservation of work and energy. Then we know if you change the internal energy of an object, then it's due to the heat or due to the work. You can have both, you can have only one. It depends on the process. So one of the important topic is the ISO process. You're going to have another calculation problem. It's going to be on the ISO process. I did show you some of the example. You should put some time to watch those video and make sure that you understand how to do those questions. So I already told you two questions you're going to expect for the exam 3 calculation. The other two calculation problem that you expect for the coming exam, one will be about the buoyancy force. So remember that we start this part, start with this fluid. So you have to know how to do the buoyancy force. That requires you to understand the free body diagram, how to analyze the force, and what is the Archimedes theory tells you, and how do we calculate the buoyancy force in the different situation. The last question that you are expect for the coming exam is going to be about the Bernoulli equation. Bernoulli equation tells you about the change of the pressure and how that will change the velocity of the fluid. And that is also based on the work and energy equation, but it's a variation, is a different way of writing the work and energy in the fluid. So you should focus on those four kinds of problem. That will be the problem that you're going to see in the exam 3. Okay, so let me work on the second law of the thermodynamics. So we talk about the zeroth law, we talk about the first law, the second law of the thermodynamics. It's about the entropy, actually. There's several different ways we can explain about the thermodynamics second law. One way to explain that is to use the engine, the heat engine. And that heat engine simply kind of tells you that there's no perfect engine that will change the heat to work. So it's not possible that you can get the heat and use all the heat to do work. You're going to lose some of the energy. And how much that you get to do the work, it's going to be the efficiency. So it's not, and so another way to say is that there's no way that you can get 100% of efficiency, meaning that you burn 100 calories, you're going to do 100 calories of the work. It's not possible in the real world. Another way to look at the second law of the thermodynamics is to use the idea called the entropy. So the entropy over here, that you can see over here, that we use a symbol called S. This capital S represents the entropy. And the rule for the entropy based on the thermodynamics law of the second thermodynamics law is that if you have like an isolated system, so this isolated system will have a change of the entropy, then the entropy will either keep at a constant or it's going to increase the entropy. And the entropy, if you read a book or watch the video or watch the pre-lecture, they will tell you what does the entropy means. The entropy, in the simple word to describe that, is represent a measure of disorder. So entropy is a measure of disorder. And what do we mean by disorder? If you watch the book, they will tell you if you have more variety of the things will happen in the same situation, that means it's more disorder. If you have more space to move around, that will be a disorder as well. For example, if you put a bottle of a perfume in a room and the perfume particle will release from the bottle, it will go into the room, it will fill in the room. Because the nature has this kind of tendency, it tends to become disorder. And that's why the perfume will evaporate and go into the room. And it's not like in natural way, the perfume particle will not go back to the bottle, right? So things is not tending to become more order, things tends to be disorder. And that measure is based on this entropy. So the entropy is a way that we measure disorder. Now, the thing you're going to do the calculation is then how do we find out how, well, since we have this property, how do we actually calculate this? There's actually two ways you can do the calculation. The book only provide one way, and that way is just simply related to our heat and also the temperature. As you can see from this picture right now on the screen, that we have two equations that you see. One equation tells you what the thermodynamics law of the second thermodynamics law tells you. Thermodynamics, the second law tells you this equation here. S represents the entropy, the delta meaning the change of the entropy. So that means you have two different states. That's why you have a change. When the entropy change, meaning the order or disorder is going to change. And because it's going to be greater or equal to 0, and that's associated whether it's going to be maintained at a constant or increase. So if you have an isolated system, meaning there's no heat exchange between the other things outside of the system simply just by itself. Then things tends to be more disordered because the change meaning the final minus initial. So you have a final entropy minus the initial entropy. That's our change of the entropy. And because entropy represents disorder, the higher of the number is more disorder. So you have the tendency to become more disorder if this is greater than 0. Okay, if that equal to 0, that means the initial disorder and the final disorder is going to be 0, and that's the maintain the constant. So entropy in natural, it has to be greater or equal to 0. But if you look at individual components, if you have two things and they change heat, and one of the object might have the change of entropy to be less than 0. However, the change of the entropy that we're looking at here, meaning the total change of entropy. So let me write a T over here to represent the total if you have a system that includes more of the object. The second thing you need to be focused on is this one here. How do we calculate that? Well, to calculate that, the change of the entropy for any of the component is equal to the Q and over the T. So this Q represents the heat that goes into the substance or the elements or the object. It's the heat that go into the object. If heat is added to the object, this one is positive. If you remove heat from the object, then this heat will be negative. This T hole over here represent temperature, but it's temperature in Kelvin. It's not in degrees Celsius, it has to be in Kelvin. Okay, so pay attention to this. If you use Celsius to do the calculation, answer will be totally different. That will be totally wrong. So make sure that you do that. Now this one also has units, so the S has the unit. If you look at the equation, you should know the unit is going to be joule over Kelvin. So the entropy has a unit is a joule over the Kelvin. Now, because we said it's not possible that you can have all the heat transfer into work, so some related topic about this chapter is also talk about the efficiency. And the efficiency is related to how much work you can actually get out of the system. So here I have another equation. This equation is to tell you if you have entropy, then can you tell us how much of the energy actually is unavailable to do the work? And that is proportional to the change of the entropy. So if you have a system become more disordered, then you will lose some of the energy which won't be able to do the work. And the amount is equal to this. So this is the third equation related to this topic. The work is not be able to do the, well, actually it's the energy that couldn't become the work is the W unavailable. That is equal to the change of the entropy of the substance multiplied with the lowest temperature of the system. Okay, it's the lowest temperature. So the temperature, because if you have an interaction between two subjects, then they must have two different temperatures. If they have the same temperature, there's no heat transfer because the thermal equilibrium. So you must have two objects that have to do two different temperature. And we're looking at the lowest temperature in this case. Okay, so that is the subject that is like a preparation for you to understand and for you to prepare to do the calculation. Let me write down one more equation. That equation is about the efficiency. I'm not going to spend time to actually explain how the heat engine, and we're not going to give you the heat engine problem, but you have to know how to use this equation. This equation tells us, well, if you have two objects, one is going to have a high temperature and the other one is going to have a low temperature. The temperature difference between these two objects is going to determine the efficiency. The E over here represents the efficiency. Efficiency doesn't have a unitless. It's just a value. This value will be less or equal to 1. And this should be equal to 0. It is that. So if you got 0.5, that means half of the efficiency. Like you give half of the energy, you give one energy, but only half of the energy will be able to do the work. So that actually tells you what? That actually tells you how much work they can do, get out of the heat that go into the system. So this is the heat to the system. And you get partial of the heat to actually perform the work. And that's how we define the efficiency. Now, this efficiency, well, most of the time we actually look at this equation to find the efficiency because it depends on the temperature. You have two different temperature, and that is how you can get out of this efficiency. Let me give you one example about this efficiency. So example about efficiency like this. Now everybody feel cold, then we will turn on our air conditioner system, even either use the heater or use the AC during the hot day. Uh, let's say that we have two different kind of a temperature, and outside of the house we have 5 degrees Celsius. Okay, now inside of the house we hope that we can have a heat pump and this heat pump is going to bring the heat into the house, and we wanted to blow air at a 40 degrees Celsius. We wanted to create a 40 degrees Celsius heat into the house. And what will be the efficiency if you have outside is 5 degrees Celsius and you have a heat pump? What is the efficiency of the heat pump in order to give us 40 degrees Celsius into the house? And you can use the efficiency equation to find out what that equation is. This efficiency equation is 1 over the ratio of the temperature. So what is the low temperature, the cold temperature? It's 5 degrees Celsius. And the high is 40 degrees Celsius. And if you write this to do the calculation, you're totally wrong. The reason is when you do this kind of calculation, all temperature has to be in Kelvin. You cannot use Celsius. So the correct way to do that is equal to 1 minus cold temperature in Kelvin. That will be 5 plus 273. And the hot is going to be 40 plus 273. And if you do this calculation, you're going to get the number is about 0.112, and that represents 11.2% of the efficiency. Okay, so and that is how you can use the efficiency in the calculation. All right, I have a half hour. I want to work through some of the example here. And let me scroll up this a little bit to start to look at the calculation. Now, just to remind you, what are the equation that we have so far? This change of entropy, this is the most important one, is equal to the Q over T. This is in Kelvin. This is in Joule. So the unit is Joule over Kelvin. Okay, let's look at the first example. The first example tells you we have an engine doing work, and it will take in 10 kJ, and the exhaust is 6 kJ, and then what is the efficiency of an engine? Well, I'm wondering why I put this one here. I think I took the wrong example, but we can also work on this one here. Okay, so let me write down the efficiency equation over here as well. Efficiency is the ratio of the work over the Q in. So it tells you that there's an engine that will do work, but it takes 10 kJ. What does a 10 kJ means in our equation? Is it represent the W or it represent the Q? Well, so you think about this, it take in, right? So it means the in, which is the heat, the 10K simply represent the Q that goes into my engine. Now it gives the exhaust, and that's the 6 kJ. So what an exhaust tells you about this engine?
It requires work.
It's the work. So if that's the work, that means it actually only do the work in that percentage, right? So this is your work that actually provide to you, and that's the heat actually generate into the house. Then you find the efficiency that will be the ratio of these two, and that will give you the efficiency of this system. So as this one is pretty simple that you can actually just take the ratio between um, these two values. So actually this is not right. Let me draw a picture over here to tell you what that is. So actually the exhaust is not the work. The exhaust is what you get, but the work is actually the difference between the heat and also the exhaust. So the exhaust is another energy, and we have an exhaust which is a 6,000 joule, and you take in 10,000 joule, and what is the amount of the work? The amount of work is the difference of these two numbers, so this will be 4,000 joule. So when you do the efficiency, you should use the 4,000 instead of using 6,000. The 6,000 is the heat that you actually received, but it's going to waste some of the energy to do the work in order to give you the heat. So the efficiency of this system is actually equal to the work, which is a 4,000 joule divided by 10,000 joule, and that will give you 0.4, or this is 40% of the efficiency. Okay, question about this part? Okay, let's look at the second one. So the second one, we're looking at a process. This is a reversible process. Now, in your pre-lecture, they talk about two different kind of process. You should understand the basic idea about the reversible and the irreversible. The reversible process refers to the mechanical energy. What are the mechanical energy? Mechanical energy are the energy of a potential and kinetic. Now, speaking about the energy, I see a lot of people still couldn't understand the difference of the kinetic energy and the momentum. And you have to know this because your final exam is certainly going to have some kind of problem about the momentum and energy. So make sure that you get the idea. Mechanical energy represent kinetic and the potential. They can transform with each other. So if you have a potential, you can make it to the kinetic, and kinetic can go back to the potential. If that is the process, then that kind of process is what we call a reversible process. One example for the reversible process is this. If you hand a small weight with a string and you raise it to a certain height, and it will swing, right? It will swing, so it will go to the other end, but it will go back to, it will swing back and forth. And that's just a way to see that you actually is a reversible process. It will change to potential and it will go back to kinetic. It will go back to potential again and go back to kinetic. So this is a reversible. However, if you drop something to the ground, if this is a ground, and you drop something to the ground, you change a potential energy to some other kind of energy. When it hits to the ground, it's no longer like kinetic energy. When it hits to the ground, it changes to some other kind of energy. This kind of energy could be acoustic energy and could be the heat, could be the thermal energy. Because that it is not possible for things to return back to certain high. This object will not go back to here. No way. An object will has an energy then go back to high altitude by itself and to release the heat. So it's not possible. So this is a reverse that kind of situation. Okay, so let's just look at this problem. So this problem said we have to have some heat and attitude to change what? To change this block of ice to water at this temperature, 270 degree, 273 degree Kelvin. That degree is 0 Celsius. But we know the ice is going to become a water at that degree. So this is what happened. I have a container, isolated container, and I have a block of ice here. This is an ice. And the ice is at the 273 Kelvin. And I add heat. I add the heat into this one here. And I will make this block of the ice become water. So this is the water. And what is the temperature of the water? Same temperature, 273 Kelvin. All right. Now we want to find what is the change of entropy. What is the change of entropy equal to? Again, you look at the equation that we have on screen. The change of entropy is simply equal to the Q over T. T, how do we calculate T in the system? We didn't tell you anything about the Q. We only give you the mass. And how do we calculate the T? Now, this one has to go back to the chapter 14 when we talk about specific heat and we talk about the change of the phase. In this case, we are actually changing the phase. We change the phase from the ice, which is a solid, into a liquid. So the key on this question is, what is the heat needed to change this phase? And in this case, because it changed phase, it is the latent heat that you need to do the calculation. So how do we calculate latent heat? Well, the latent heat is equal to plus or minus times the mass times the latent heat. And we have two kinds of latent heat. We have a latent heat of fusion. We have a latent heat of vaporization. And positive or negative is depends on whether you need heat, you have to add heat, or you remove heat. If you add heat, it's going to be positive. If you remove heat, it will be negative. So this one, we are looking at the solid to liquid. So that is the fusion. If you are looking at the liquid to gas, that's the vaporization. So this one, we are looking at the fusion. This is the LF. Okay, so when you do this calculation, you have to go back to look at the chapter 14. There's a table to tell you different material have the different fusion latent heat. And let me look at my table. I am not going to, you can find the table by yourself. See, I have the table here. I will just get the value. Okay, so I find out this latent heat of the fusion is 334 times 10 to the 3. Unit for this is the joule divided by kilogram. So that's the latent heat. Now, in order to get that, I also need to know the mass. Well, the mass is given is 500 grams, but you have to convert this one to kilograms. So this is 0.500 kilogram. And you multiply these two, it's going to give you the heat that is needed to change that. And because this is a change from solid to liquid, from ice to water, so you need to add heat, because it's add heat is going to be positive. So this is going to be positive, and you multiply these two, that's going to give you 167 times 10 to the third joule, and that's just joule. That is the energy. Kilogram will cancel out. All right, once you have this, then we can calculate the delta S, right? Delta S is equal to the Q in over T, and this is 167 times 10 to the 3 joule over 273 Kelvin. And that will give you the result. 612 joule over K is the change of the entropy. Okay, so that is one example to show you how to do this entropy, the change of entropy. Let's look at the second one. Okay, here I need to make this one change. This is to the third. This is to the third. This is the volume. One more of ideal gas expand isothermally from 1 meter cube to 2 meter cube. And what is the entropy change for the gas? Okay, what does isothermal means to you? We have several different iso processes. You have to know the definition for each one of the iso process. Isothermal is the simplest one. You know the thermal represent the temperature. So isothermal meaning temperature is a constant. And it doesn't tell me what temperature that is, but it just simply tells me temperature is a constant. And then it tells me it expands from 1 to 2 meter cube. But we want to find a change of entropy, which is equal to the Q in over T. Now we don't know T, we don't know Q. So how do we work on this? And this one, you have to go to watch our previous lecture. We talk about the Q for different processes. Okay, just a little bit quick review about if you have an adiabatic process, the Q is equal to 0. If you have an isothermal process meaning the change of internal energy is equal to 0, and that is equal to your Q minus W. Okay, and the isothermal energy for the Q is going to be equal to the work. So that simply means you have to find a work for the isothermal process, and that's equal to your Q. And what is the isothermal work equal to? The isothermal work is MRT nature log VF over VI. Okay, if this is a new to you, that means you should watch the video from the previous lecture. So this is the work only for isothermal process for ideal gas. Okay, in all only a certain situation that you can use this equation. And but again, I don't know the temperature, right? This only tell me the work, and it didn't tell me the temperature. It did tell me this is a 1 more, which means this is equal to 1. And this is a constant, this is a 8.314. And the unit for that is the joule per mole and K. And the final volume is 2 meter cube. Initial is 1 meter cube. Doesn't tell me the temperature, but let's just put everything together. This is equal to your Q. So our change of entropy is equal to the Q, which is equal to W, which is N RT nature log 2 over 1 meter cube. It will be canceled out anyway. And the bottom thing is going to be the temperature. And you see, even though we didn't tell you the temperature, but the temperature will be canceled out. And this one equal to 1, this one equal to 8.314, and nature log of 2 over 1, then you can get the result. So the result for this is going to be the, you can put the calculator. Let's see, I have that or not. Yep. That will be 5.76 joule per K. Question about this? Can you guys still hear me?
Yes, I can hear you.
Okay, thank you. Okay, let's do the last one here. Okay. So the last one here is one of the homework problem. If you work on the homework problem, this one is a little bit complicated. Now the number that you get from the homework will be different from the number that I show you at here. I just want to give you an idea how you do the calculation for this case. So suppose that you have two large reservoir of water. So one has a 93 degrees Celsius, one is 19 degrees Celsius. And you put them together and then we'll have a thermal contact and then they're going to have a heat transfer. So what I mean is that I have a hot reservoir here. I have a cold reservoir here. And the hot one is 93 degrees Celsius. The cold one is 19 degrees Celsius. And the thermodynamics law tell us the heat is transferred from high to low. So I'm going to have the heat that goes from the hot to the cold. So there's the heat, the Q. This Q is equal to 41010 joule. And we're going to assume this reservoir is very big, even though there's like a heat transfer from one side to another, it doesn't change the temperature a lot. If you do have the temperature change, and it's quite a lot, when you do this calculation, the change of the S, this one, you can use the temperature of average. If you do have a change of temperature quite a bit, then you use the T average. The T average is simply just like a T initial plus 2 final divided by 2. That is the average temperature. What is the total change in entropy? When you see a total, meaning there's have several different components in the system, and the two component system, in this case, is the hot reservoir and the cold reservoir. So you're going to calculate this one based on two change of S. And so what is the hot object heat equal to? It gives you this number here. This number is the heat goes into the cold one. And that means the hot one is going to lose the heat. So over here, you should put the negative 41010 because it loses heat. What is the temperature of that? Well, the temperature is now 93. You have to be 93 plus 273. That will give you the Kelvin. So that's the heat. That is the change of entropy of the hot object. You also have the cold object. The cold object is going to gain heat, so that heat is the same number, but it's positive. But the temperature is also different. Temperature is 19 degree plus 273 in Kelvin, and then you can get the calculation of this. If this is a process will happen naturally, spontaneously, this one should be greater or equal to 0. That is the thermodynamics law, the second thermodynamics. Okay, so what about work? Well, if you remember the unavailable work that we mentioned at the beginning of the course, it's equal to the change of entropy times the T of the lowest in Kelvin, okay, in Kelvin. And because change of S is the heat over the temperature, so this one is refers to the total. So what is this one here equal to? If you look at this question, that's equal to 28.4, and you multiply with the lowest temperature. And then what is the lowest temperature in this case? Well, it's 19 degrees Celsius, right? So you multiply with 19 plus 271 and 273. And that will give you the number in joule. And that will be equal to 8290. Okay. All right. So what about the next one? The next one that we are asking is how much work could an engine to do to take a given amount of that heat from the hot water to the cold and exhaust the heat to the cold reservoir. So the exhaust is actually goes to the reservoir. Then how do you calculate this? And you just think about the one that we just told you. If you have the heat goes in and it goes to the engine, and it'll give you the exhaust, and this is the work. So if you know the exhaust and if you know the a variable is the exhaust, then you can figure out what is the work actually done by the engine. So the work of the engine is actually equal to this. It is the heat that brings it into the system times the efficiency of the system. But what is the efficiency? Well, the efficiency that we just mentioned before, this E is equal to 1 minus hot temperature to the low temperature. Oh, no, this is a cold temperature. Work of the engine, you need to find the efficiency and you multiply with the heat that goes in. So this is the heat in, this is the 41,000 joule, and the E that you have to get from the temperature difference. Now, this T here is also in Kelvin. I emphasized this before, so I just wanted to make sure this time nobody make mistake on this.
Professor, can you scroll down?
Oh, okay. Yeah, sorry.
Yeah.
Yeah, thank you. Okay. So, so I'm trying to calculate the efficiency. It's 1 minus the code. The code is 19 degree plus 273, and hot is 93 plus 273. And that's how you get the efficiency of that. And then you can use that efficiency multiply with 41010, and that will be the heat. That will be the work of the engine. Okay. Okay, 2 minutes. Let me just quickly tell you about this, the last one here. So the last one is also your homework problems that tells you one person that will typically eat something, some amount of the heat per day, but only certain amount of the heat will be actually to be the heat, and some of them is going to become the mechanical energy. So what I mean is the actual heat that will change your entropy is not 100%. It's not going to be equal to 2250. Then how do you do that? Calorie. You multiply with the percentage, they actually become a heat, right? So this is actually the heat in, because some of the heat become a work. And that will be 100% minus 25.5, because we know 25.5 become work. And that will be the percentage of the heat actually gets in. Now this, if you calculate this one will be in cal, but you have to convert this one into a joule. So how do we convert that? Well, 1 calorie is equal to 4.184 joule. So you have to multiply this in order to convert this into a joule. So that will give you the number in joule, okay? Now, if you wanted to use the kjoule and was specified by this question, then you just take out the 1,000 and just simply say this is a kjoule, and this will be k calorie, and that will be kjoule as well. So this will become okay. Now, once you get a Q, and how do you find the delta S? Well, same equation. You have the Q in, which is the value that you calculate from the previous step. Then the temperature is 20.5 degrees Celsius, but you have to convert it into the Kelvin. So 20.5 plus 273 is the number that you put. Is the material for today, and I hope this will give you a good idea how to calculate the change of the entropy. All right, I'm going to see you on Monday. So remember, please join me to the Zoom meeting on Monday. And we start at 1 as well. So we start from 1 to 4 o'clock. I'll see you next time.
Thank you, Professor.
Thank you.
Hi, Professor.
All right.
Hello.
Yeah.
I just so do you have,
Okay. Yeah, I got you. So you want to see your exam?
Yeah.
Okay. I'm gonna wait until people.
Office
Yeah,
hours?
I'll wait until people left, and so I can show you your exam.
Okay. And we don't have lab on Monday, you said?
Yeah. So no lab on Monday. Just join the Zoom. I'll
Okay.
send out email about the Zoom link.
All right.
Okay, let me get your exam. Oh, I hope I bring it back.
Yeah, I got there at like exact 11:30, and you
Okay, I just left because I tried to get home. I forgot to bring my pad, so I couldn't write.
okay.
Let me see yours. I'll turn on the I'll turn on the video, then you can watch that, and you can take a screenshot if you wanted to. Okay. Turn on my video. I didn't know that you grow bear.
Right.
Nice. How do I show you? Can you see us? Wow.
No, I can't see you. Like I could see you like so I saw you.
My yeah, unfortunately, my system freeze now. Uh,
So I mean, if you can scan it and then send it to me, that's fine as well.
uh, can I close and then can you join again?
Yeah. So on the same meeting, right?
Yeah. Send one. Okay.
Okay, sure.
Close it. Okay. Shoot. Oh man. June.
Oh, you joined from another